So now we're going to start talking about two very important data structures, stacks and queues. In this video, we're going to talk about stacks. So what is a stack? It's an abstract data type, and here are the operations we have. We can push a key. So we've got a collection of values, and we can push it. We can find the most recently added key with top, and we can pop, which removes and returns the most recently added. So the way to think of it is as if you have a stack of books. You can put a book on top of the stack, or you can take a book from the top of the stack. But you can't take the element at the bottom of the stack of books without taking off all of the previous elements. So it's really pretty simple. You can push items on, you can find where the top one is, you can pop off the top one, and you can intermingle these operations. Okay? The last one you can find is it empty? So do we have an empty stack? This turns out to be really useful for lots and lots of things where you need to keep track of what has happened in this particular order. Let's look at an example. So let's say we've got a balanced brackets problem. So here we have a string, and it has left parens, right parens, left square brackets, and right square brackets. And we want to return whether or not that string of parentheses and square brackets, whether they're balanced. Okay, balanced meaning there's a matching left paren for every right paren, and they're in the right order, and they don't cross over. Let's look at some examples of balanced. So the first string here, left paren, square bracket, matching square bracket, matching right paren, square bracket, matching square bracket, right paren, left paren, matching paren. Balanced. The second one, also balanced. The unbalanced one, for example here, we have a left paren with no matching right paren, assuming that the two parens on the right side are matching themselves. The square brackets match, but then we've got an unmatched right bracket. Or in the last case, we've got a square left bracket and a square right bracket, but the problem is they're in the wrong order. It's a square right bracket followed by the square left bracket. Okay, so how do we keep track of that? And the problem is, in some cases, we have to kind of keep track of a lot of information. So for instance, in the second example here, we've got our opening left paren doesn't get matched for the right paren for quite a while. There's a lot of intervening stuff. And we have to sort of keep track that we've got a left paren whose right paren we need to match, even as all this other stuff happens. And it turns out a stack is a good way to keep track of that. So here's what we'll do. We'll create a stack, and then we'll go through every character in the string. If we have an opening paren or an opening square bracket, we'll go ahead and push it on the stack. So the stack is going to represent the parens that are still open, the parens and brackets which have yet to be matched, and the order in which they need to be matched. So the outermost ones will be at the bottom of the stack, and the last one we saw, the innermost one, will be at the top of the stack. Then, if it's not one of these opening ones, then if our stack is empty, that's a problem, because basically we've got a closing paren or bracket, and there's no matching element. So if the stack is empty, no, we're not balanced. Otherwise, we'll pop the top element off, and then we'll check and see, does it match that element from the stack? Does it match the character we've got? So if the top was a left paren, did we just read a right paren? If so, great. They match, and now those two match. The next one we need to match is still the newly top one on the stack. Or similarly, if we have a square bracket on the stack and a square bracket we read, those match as well. If they don't match, then we've got a problem, right? If we've got a right paren on the stack and a left paren on the stack and a right bracket that we just read, those don't match, for example. So then we'll return false. Once we've run through all of the strings, we're matched, right? No, not necessarily. Imagine we had the string left paren, left paren, left paren. We'd go through, we'd push a left paren, we'd push a left paren, we'd push a left paren, and then we'd be done. We wouldn't have returned false. But it's no good because we didn't actually match what's on the stack. So once we go through all of the characters in the string, then we've got to actually check and make sure, is our stack empty? Did we successfully match everything? This is only one example of the use of stacks. Stacks are used in lots of other places. They're used for compilers. They're used in a lot of algorithms that you'll be seeing throughout this course. So how do you actually implement a stack? Well, let's look. You can implement a stack with an array fairly easily. So allocate an array of some maximum stack size. Right? So in this case, we decided it's 5, just for the sake of example. And we're going to keep a variable, which is the number of elements that are actually in the stack. When we push, so in this case, we're going to push A, we're going to go ahead and put it at the end of the array we've got so far. So for whatever elements we have, we'll append it to those. So in this case, we'll put it at the beginning of the array, because we haven't used any elements. And we'll keep track, the number of elements is 1. Okay. We push B, we'll put it at the next spot, and our number of elements is 2. Fairly straightforward, right? We're just appending to the array. And these are clearly order 1 operations. What's the top element? Well, that's really simple. If the number of elements is 2, that means we need the second element from the array, which in this case is B. Again, a constant time operation. We push C, our number of elements is 3. And now let's say we pop. Well, what do? We need to go get the third element, which is C, and erase it, and then adjust num elements so it's now 2. Now we can push an element, push another element, push a fifth element, and now if we try to push again, that's an error, right? Because we don't have any more space, so that wouldn't be allowed. Is it empty? No. How do we know? Because the number of elements is greater than 0. Again, an order 1 operation. And now we can start popping, which will be returning the appropriate element of the array based on the num elements value, and keep popping until we get down to no elements. Okay? If we're at no elements and we ask it's empty, yes, that's true. We can also implement a stack with a linked list. So one disadvantage we saw, one limitation of the array is that we have a maximum size based on the array we initially allocated. Okay? But all the operations are order 1, which is good. The other potential problem is that we have potentially wasted space. So if we allocated a very large array, okay, to allow a possibly large stack, but we didn't actually use much of it, all the rest of it is wasted. If we have a linked list, what we do then is every element in the list, of course, will represent a particular element in the stack. And so we'll push A. And then if we push B, we're going to go ahead and push B at the front. So basically pushes will turn into push front. If we want to get the top element, just get the head element. Okay, so top will really just be top front. We can keep pushing at the front, or popping. All of those are order 1 operations. We can keep pushing, and the nice thing about this is there's no a priori limit as to the number of elements you can add. As long as you have available memory, you can keep adding. There's an overhead though, right? In the array, we have each element size is just big enough to store our key. Here, we've got the overhead of storing a pointer as well. On the other hand, there's no wasted space in terms of allocated space that isn't actually being used. So we keep pushing. Is it empty? No, because the head is not nil. Okay. And then we can go ahead and pop. So if we had a linked list, it's very simple to implement the linked list operations in terms of the linked list operations. Push becomes push front, top becomes top front, and pop, which is supposed to both return and pop the top element, can become a combination of a top front followed by a pop front. Empty is just empty. Okay, we keep popping, and then eventually we pop the last element, and now if we ask whether it's empty, the answer will be true. Okay, so that's our stack implementation. Stacks can be implemented with either arrays or linked lists. I've talked a little bit about the pros and cons of each of those. The linked list has a fixed amount of overhead. That is, for every element you are pushing, you have an additional pointer. For arrays, you have potentially space that you've over-allocated, basically, to allow for a stack to grow to a maximum size. For arrays, stacks do have a maximum size. For linked lists, they don't. Each stack operation is constant time for either one of these implementations. Sometimes we know stacks as LIFO queues. LIFO meaning last in, first out. The last one that was inserted is the first one that comes out. This reminds me sometimes of also what's known as GIGO, garbage in, garbage out, that if you input garbage into a system, you get garbage out. But this, of course, is different. So that is stacks. In the next video, we're going to go ahead and look at queues. Thanks.